Hey there. Gonna do some math here. Some good math. I don't know. It's interesting, I guess. Hey, do you have any of your reference sheets? Because you don't need those today. Right. All right, moving on. We're gonna do lesson 84 this day, whatever, Monday, Friday, whatever when it is you're doing this. Lesson 84, we're gonna be solving rational equations. And I got over here the methods we're going to use for examples 1, 2, and 3. There's also an application question, which is a little weird, but it's a rate, distance, time type of equation. But starting with something else, let's start off topic first, or slightly off topic, and that would be rational functions. Functions like f of x, and our most basic rational or fraction-containing function would be 1 over x. 1 over x. It's pretty cool. It's pretty basic. It does play into lots of things in math world, and it's one of the first types of equations where we find out that things are broken sometimes. That is, what if x is 0, right? You get a function that's broken at some place. And if you were to graph this on your thingamabobber, it goes like this, and then just drops off, and then here it comes again. And it goes like that. So at 0, here it has an asymptote, a vertical asymptote, where it is undefined. Also, it has a horizontal asymptote. It'll never get to 0. No matter how far you go negative, no matter how far you get positive, it'll always be 1 divided by something, even if that's something super duper huge. So that's a problem. Also, if you start listing off the plug in one at a time into a sequence, like 1 over 1, and then 1 over 2, and then 1 over 3, etc. That's called the harmonic sequence. And there's some cool things that happen if you add all of these up. We'll talk about that in pre-calculus when we do some sequences and series. Okay, so that's called the harmonic sequence. These are the fractions at which you get harmonics in music. Thirds, fifths, sevenths, things like that. You're thinking like how chords work. So that's pretty useful, at least when x is an integer. But again, these types of functions can do funny things. Case in point, you have a function like g of x equals. Something like that. It has holes. If I plug in a 2, this thing breaks down. If I plug in a negative 2, well, it still works, right? But the weird thing about this one is we've got the difference of 2 squares, and so we'd have x minus 2, x plus 2 over x minus 2. I want you to know that this expression here and this expression here may look the same if you graph them, but they will be different if you go to analyze them. That is, this thing right here will look like a line, and this thing right here will look like the exact same line. But this one right here, if you go to 2, it actually has a hole in it. You go to trace it, and you type in, let's see what happens at 2. It won't have an answer there, though this one will. So canceling in rational expressions, rational equations, changes things. Okay, you need to always go back and look at the original problem and see if you have any problems in there, any breaks, any holes, any asymptotes, discontinuities. Right, so anyway, we're going to be dealing with then rational equations. Rational equations. And people always say, well, why do we need to do this? Because rational equations can be used to make rational functions, and those have special things that we need to consider. So if we write something like 30 over x squared minus 25 equals 3 over x minus 5. When I look at that right at face value, I think there's some factoring that could be done here. X minus 5, x plus 5. And then that means that there's at least one common factor here of x minus 5, there's a couple of ways that I could tackle this equation right here. Now, if I'm graphing it, this one will be one type of graph, and this will be another type of graph. We'd be looking for a solution is going to be the places where they interact with each other, where they crisscross each other. They share answers in common. All right, well, we're trying to solve this expression here, this equation. And you can see that number 1 I can cross multiply. But I could also apply number 2 to this. Let's find the greatest common denominator. Let's multiply through by common denominators to get rid of fractions, right? And 3, I see that I could do some factoring in here too. So I could take the same problem and attack it in 3 different ways. Let's try method number 1, which involves cross multiplication. Let's go ahead and let's multiply 30 by x minus 5 and 3 by x squared minus 25. If I do that, I get 30x minus 150 on the left. I get 3x squared minus 75 on the right. I would need to bring them all to one side. 3x squared minus 30x plus 75 equals 0. And then I got a quadratic that I can solve. Everything's divisible by 3. That's a perfect square right there, isn't it? I believe that is x minus 5 squared. And so 5 is one of our answers for x. Now what's the other one? Well, looking back at the original equation, negative 5 would make this thing equal 0 as well, right? Well, looking back to right here, negative 5 squared minus 25 would also be a solution. Now, at first, this one checks with a 5er in there. A little weird on the checking because the original here would make this equal 30 divided by 0, and a 5 would also say the same thing. All right, a little funky, a little whatchamacallit. What does the book do with that? It says it's extraneous and it doesn't have any real solutions. No real solutions. Okay, so we say we checked extraneous. So it might be a good idea right at the beginning to look at the thing and say, well, what would make this thing break? 5 would make this thing break for sure, because that would make denominators equal to 0. We're not allowed to divide by 0. Look back at the original expression and see what it does. Now, if we stopped here, we'd say, oh, nothing wrong here, but it's not the same thing as this expression right there. So we can do some cross multiplication to try to come to a solution, but then you have to check. You have to check. These are rational equations, which means they've got denominators that might have broken parts. Cross multiplication. Yeah, let's look at one more where maybe we could do that, or at least think about some methods here for this. X over x minus 5. Okay, you can also cross multiply. I got another trick up my sleeve, and that would be to multiply this by negative 1 over negative 1. If I do that, I'll get... Now we can see that these two are the same. So negative 9 must be my answer for x. That's kind of a little trick. Now, let me go back to the original expression, and we can cross multiply. 9x minus 5 equals x times 5 minus x. Doesn't look different. Well, it does kind of. 9x minus 45 equals 5x minus x squared. Let's put everything over here. We got x squared and 4x minus 45. Let's see if we could solve that, but it was easy enough to just have done the switcheroo thing that I just did. Because at this point, we're trying to factor this out. 45's negative 45, 9 and 5, right? X minus 9, x minus plus 9 minus 5. And then so we get x equals negative 9 or positive 5. But look at the original problem. Does 5 work? No, 5's a problem. 5 minus 5 is 0. 9 divided by 0 is undefined. So we have to take off that one, and we can only use this one. You got to check on these ones because they have broken pieces. Oh, yeah. That's right. All right, let me get a couple more up here, and off we go. Okay, Zach and Dutch, this is going to be weird when you watch this because you already heard me say this. And then when I say this, you'll be like, yeah, we were there when he said that and stuff. Well, I'm going to keep going because, you know, the day's moving on.
Oh.
What?
On our YouTube deal, it doesn't say that I beat it, even though I watch it.
Yeah,
oh, okay.
So it might look like there's
Some of them I put there only for children. Some of them I put that anybody can watch it. So I don't know if that makes a difference.
I don't know if that's 'cause I got on an account or what. But
Yeah, I don't know.
I watched the review video for Bible today to listen to my dirt bike, but I couldn't hear it. But when I watched it, it said it still had the reviews.
Oh, well, bummer. Well, I do get, it does keep track of them, so. That's weird. All right, here, one thing that we almost always want to do with fractions is we want to get rid of fractions. So the way you get rid of fractions is to multiply through by a common denominator. And here the only denominator is the factor x minus 9. So if I do that, and basically I got to do it to both sides. I can write it like this, or I could write it like this. I kind of like this. You just multiply it all the way through on both sides of it. So that there will cancel out. You'll have 10x. And then over here, you'll have 15 times x minus 9. It does the same thing as cross multiplying or moving this to the other side. It just kind of looks cooler. So we got 10x equals 15x minus... Hey, what's 15 times 9?
135.
135. I knew that. Okay, so we got that 5x equals 135. Now we're thinking about like 135 divided by 5. That would be 27. Then double check, make sure that jives with this. Looks like 27 is an okay number there. Oh shoot, that's not the right answer. 15x minus 5x. That's 5x minus 10x and 135. Yeah, 27. What am I thinking? 27 is the right answer. I go and check on 27. 10 times 27 is 270. And divide by 27 minus 9. That's just 18. 270 over 18, I think, equals 15. So that one actually checks out. No extraneous weirdo-ness there on that one. But I know that if I got the answer 9, it wasn't going to work, right? Because the original problem had this in it right there. So if we got 9, we should have been suspicious about that problem. You were, but you didn't have to wait. Oh, but it's simple. All right, this one looks suspiciously simple, but it's not. If I'm going to use number 2, method number 2, I'm going to multiply everything through by x, and that gives me an 8 there, and it gives me a 2x there, and it gives me an x squared there, which smells suspiciously quadratic. So x squared minus 2x minus 8 equals 0. And then hopefully I can factor this bad boy down. I think this is a minus 4 and a plus 2. So x is 4 or negative 2. Is that gonna mess up anything here? 4 and negative 2 I think works. Only thing it can't be is 0. I think both of those check out. Here's one that I'm going to tackle in a different way. Cross multiplication is not really going to work here because we've got sums, right? And even if we move something over, it's still pretty messy. So what we're going to do is we're going to move on from multiplying. Well, I guess we could do number 2, but this one kind of lends itself to number, well, 2 or 3, I'd have to say. Okay, so let's imagine here we're just going to apply a new method here. So I see this right away, and I'm thinking, can I factor that? Is it factorable? I got 3 and 5, right? And that would be a better way to think about this one rather than this quadratic. Let's just plug that in. Let's put an x plus 3 and an x plus 5 there instead. And now it doesn't look so bad because we could just multiply through by both of these. That would, I guess, be method 1, which involves, well, I mean method 2 would be the first thing that I might try. Okay, but factoring was involved there, and then I could go ahead and do that. Or I can go ahead and just make sure that all 3 of these have the same denominator, which is the same thing as multiplying through by the greatest common denominator. This one here needs another x plus 5. This one here is fine, and this one here needs both x plus 3 and x plus 5. So you'd start doing stuff like this. And over here, we need an x plus 3 and an x plus 5. So that would take care of all of those. We don't need the same denominator anymore because we've done the whole thing, haven't we? So we got this, and then this, and this, all without denominators, and then we can go ahead and we can solve that thing. Okay? That is a quick way to do it and get rid of denominators. But first is to be identifying that there's some factoring that's involved there. X squared plus 10x plus 25 plus 28 equals 4 times whatever that quadratic thing was right there, and then going through and solving the rest of the business. I'm not going to finish that off. That one's there in the book. You can see that that it took a lot of pencil work. It's hard to make the same face there after I moved and stuff. Okay, let's take the very last problem, the application problem. It's a word problem that you kind of have to write as a rational equation. An athlete runs 12 kilometers on Saturday. That's a distance, just in case you didn't know that. And bikes 30 kilometers on Sunday. The total time spent working out was 4 hours. Find the time spent working out each day if the rate of travel on Sunday was twice what it was on Saturday. Okay, and here we have to remember that distance equals rate times time. Rates are things like miles per hour. So really we're looking at the fact that rate equals distance divided by time. But oftentimes these things are phrased this way. The distance is going to be a rate multiplied by a time. Okay, well, the distances are 12 and 30. So they're going to have to be on opposite sides here. 12 and 30. Now, write an expression for the rate of travel on each day. Oh, man. Okay. The rate on Sunday was twice of what it was on Saturday. So, let's see. Distance over time equals rates. Distance over rates equal times. That's probably what we need to look at. And so the rates, one day was twice the rate of the other. The total time spent working out was 4 hours. Time on one day plus time on the other day equals 4. So, let's do it like this too. Distance over rate equals time. That's probably what I need to think of here. So here's distance 1 and here's distance 2. And now I need to find out what the rates of these things happen to be. I know that if I add these two together, I'll get 4. Or I suppose if I want to have the t2 over here, that's the way that's going to have to go. First time equals 4 minus time 2. This minus, I guess we have to have 4. 4 minus time 2, which there was 30, right? You could think of it like this. Okay, 4 minus t. Oh, these multiplies. Rates and times equals distances. Hang on. Sorry, I needed like 30 seconds of cogitating. Okay, we got to express the rates on each day as distance over time. And then we'll see how they jive with each other. The rate on Saturday is 12. That's my distance, divided by time. And the rate on Sunday is 30 divided by the rest of the time. Remember, the whole thing's 4 hours. So 4 hours minus whatever happened on Saturday equals what happens on Sunday. And then lastly, they say that the rate on Sunday was twice what it was on Saturday. So if we double the Saturday thing, we'll say this one needs to be twice as much so that it can match that one over there. Low, but there it is. Okay? Twice of the rate on Saturday equals the one on Sunday, because Sunday is going faster. Okay, so this is 24t equals 30 over 4 minus t. This looks like a cross multiplication type of problem for you. 24 times 4 minus t equals 30t, and then off we go for solving the problem. 96 minus 24t equals 30t. 96 equals 54t, and then finishing it off, and what do they get? 1.77777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777777. There's probably other ways you can work this one out, but it's based off of these facts here. Pick the one that seems to fit the best. I could probably think about this for a couple minutes and find a different way to do it. But nevertheless, there you are. If I assign G, it requires something like that. You need some help with it. I'll probably have an idea of what to do by the time you give me a call. All right, there's your lesson 84. Good luck with that on Tuesday. And math chat time if you want to in between.